Hey there, Calc 3 folks, back here with another video in this sequence in our study of vector-valued functions, where in my last video, if you're following along with these chronologically, I looked at the derivative of vector-valued functions and gave a quick little video over that topic. And with the presentation of the derivative, with the defining of the derivative, that brings up the idea of what we might think of as an inverse operation to differentiation, and we should be familiar with that operation known as what? The antiderivative or anti-differentiation, or what we sometimes call integration, right? What we need to look at next is then the integral of vector-valued functions, and what we're going to see presented, first of all, is going to be very analogous to what we've understood back in the days of Calc 1, right? At the end of the semester there, when we learned a little bit about the integral operator. And then some of it's going to be analogous to what we saw happen or I should really say similar to what we saw happen in the case of applying and finding the derivative operator of a vector-valued function. All right, so let's get into it here. Let me bring this up. Here's our notes, as always, and you can see what I start with is recalling a little bit of our past knowledge from Calc 1. All right, we understand from Calc 1 that if we are given some function y equals f of x, applying the integral operator to this function yields the following result. That result being this statement right here. If we take a function f of x and we apply to it this integral operation, right? We understand that result is itself a function of x. A function of x that's related to little f of x. That's why we call it here in the notation big F of x. And how it's related to little f of x is that is little f of x is what we say is antiderivative. Right? This is where big F of x is the antiderivative of little f of x, meaning, right? Certainly meaning that f prime, when you take its first derivative, you will obtain that function little f of x. And in this format, not only do we get, when finding an indefinite integral, the antiderivative big F of x, what we should understand is not only do we get a single answer here, we actually obtain a family of solutions, all of which differ by the result of a constant. So when we think about applying this indefinite integral operator to a function little f, the result is going to be a family of solutions with this constant being added to the end, right? So c is any constant value. Likewise, if we flip on the switch and make it a definite integral and place some bounds on our integration there, right? We are going to now use this antiderivative operator along with these bounds, and what we say is evaluate the antiderivative across those bounds. What we mean by that is we are going to evaluate big F at the upper bound of B and subtract from it the value of big F at the lower bound of A. All right? It's called evaluating our antiderivative across those bounds from A to B. When we calculate a definite integral, that's what we're doing. We're taking the antiderivative that we would find big F of x in the case for the indefinite integral and evaluating it across those bounds, evaluating it at our upper bound and finding its difference from the lower bound, subtracting away its value at the lower bound. All right? Now that's Calc 1 idea. End of Calc 1, we got into that idea. And this does come back with an analogous idea now with the context of vectors and the vector-valued function r bar, where I present this in the following definition. Here's our definition. And it does look very similar to what I just presented above. All right? Given the vector valued function r bar of t in some n-dimensional space, the indefinite integral of r bar, right, is given by this statement here, where we're just applying the indefinite integral operator, right, to our vector valued function r bar of t, and applying it with respect to the parameter t. Right? Now the result of that is going to be a family of solutions, which is what we see on the right-hand side. There's some uniqueness to that family of solutions. First of all, it's going to involve capital R bar of t, where a lot like with the Calc 1 idea, we are saying this is going to produce another function of t that is related to little r. That being that big R of t is big R bar of t is related to little r bar of t as its antiderivative value. Right? Meaning that if we took its derivative as a vector valued function, it would result in little r of t. Now, as we highlighted in Calc 1, not only do we get one solution, we get a family of solutions, all of which differ by a constant. And in the case of a vector valued function, we just don't get a scalar valued constant. What we get is a constant vector whose dimensions match the dimensions of the vector valued function over which we're integrating, right? The dimensions of our constant vector c match the dimensions of r bar in our interpretation here in the definition. All right? And similarly, if we were to calculate a definite integral of r bar, a t over t in some closed interval from a to b, right? That is given by this notation seen here on the far left-hand side. If I can highlight it, it's not going to let me. But it's this quantity seen here on the far left-hand side, right? Where what we are going to do is evaluate the antiderivative of little r bar, which is itself a vector, right, across those bounds from a to b, right? Much like we did with the scalar value case for the function. All right? If we consider how that actually will apply, we see a rather intuitive idea that follows from how the derivative operator applied itself. All right? As for applying the integral operator to a vector valued function in n-dimensional space, as with the derivative operator, the integral operator distributes itself across the components of our vector valued function. All right? If we were to consider the case in 2 dimensions, where r bar of t is equal to x of t comma y of t in our 2-dimensional space, when we apply the indefinite integral operator to that result, that integral operator will just distribute itself across those components. And what you will be left with doing is integrating, right, the scalar value functions found in the components of the vector valued function. Right? This integral operator just distributes itself throughout the components of the integral. And that happens both in 2 dimensions, in 3 dimensions, as we see here in our similar statement, and it happens in n dimensions. Likewise, if we were to evaluate a definite integral, the indefinite integral operator would distribute itself. And we might even say that here. Likewise, for the cases of the definite integral operator, we'll say operation, the definite integral is distributed across the components of the vector. All right? Vector function. Let's get a little bit more specific there. All right? So let's add that note. And then let's just add a quick notation bit here. So let's grab this case up here. All right? the integral from a to b for r bar of t dt, right, is equal to just the integral from a to b for with respect to t, where I'm going to substitute in this vector valued function, right? And then what am I going to do with that? I'm going to distribute that integral operator from a to b to the scalar valued function x of t dt. And I'm going to distribute that integral operator to the second component, the scalar valued function y of t, and integrate it definitely with respect to t over that interval from a to b. Right? That would be the similar result we would see in the case for a definite integral. Forgot to think I add that in there, and let's put that in there just so that it's clear for everybody. And give us a little bit of play on notation and flow and nature of approach. This is kind of a good way to think about approaching showing some work for these problems. Let's actually look at a problem. Consider finding the indefinite integral of r bar of t dt for the vector valued function given by this two-dimensional vector. The first component is the quadratic t squared minus 5t plus 2. The second component is this product involving a composition here, t times the cosine of t squared. If we apply the indefinite integral operator to that vector function, it will just distribute itself across the scalar value functions found in each component. Right? It will distribute itself to this first component, and it will distribute itself to the second component. And what we will be left with is finding these two scalar value indefinite integral calculations. Right? Indefinite integral calculations that we could do back at the end of Calculus 1. Both of these are calculations that are Calc 1 calculations. These may have been on a final exam. But in the context of f of x, not what? X of t and y of t, functions of t. All right. Nonetheless, this first one, how do we get through that? It's fundamentals. That's fundamental rules. A little sum and difference rule and power rule and constant multiple rule in there, folks. The antiderivative of t squared minus 5t plus 2 is what? 1/3 t cubed minus 5/2 t plus 5/2 t squared plus 2t. Right? The little power rule there, this power at 2 bumps up to 3, and we divide by that power of 3. I like to do a fractional multiple instead. This first power at t bumps up to 2, right? And we divide by that 2, making this into negative 5/2. 2 has a power at t that is t to the 0 power, so it bumps up to 1, and we divide by 1, and that's just 2t. And then don't forget to add on your constant. Now, we're going to see a couple of constants appear in these individual calculations, so let's call this one constant 1. You'll see why in a moment. All right? And if we go into the second integral calculation here, well, how are we going to get through that? That is going to be, what here? A little variable substitution. All right, we notice a little u substitution should work here. If we let u be the quantity inside this integrand, t squared, then du dt will equal 2t in value. So 1/2 du would equal t dt in value, and this t dt could get replaced with 1/2 du if I replace this t squared with the quantity of u. We set up a u substitution. This is the end of Calc 1, folks. You should be familiar with this process. And that's what I'm laying out for you here in brevity. All right? And what that does imply now is if I find this antiderivative, well, cosine of u is sine of u for an antiderivative. So this turns into 1/2 sine of u plus another constant. And this is why we're using subscripts, because here we get a second constant. It's not the same as the first. All right. But certainly in u substitution, we don't want to leave the u in our answer. We need to go back and note that u was t squared. So we plug t squared into that and we get this result here. Now, if we go back and organize that in our final result, when we think about then the actual antiderivative or indefinite integral calculation of r bar of t, and when we distribute it across those two components, this would be the result found in each component. Where you'll notice it has the antiderivative calculation plus some constant in each component. Where what we would be able to do is actually isolate these two constants by subtracting them from these two components as a constant vector itself, as actually the constant vector c bar, which I make note of here in the notes. You can see those constants go away from here, and c bar becomes this constant vector c1 comma c2. Whereas what this other portion is that we're adding in to c bar, well, that's big bar bar of t. That is the antiderivative vector for little r bar of t. It's the vector whose first derivative would yield little r bar. Right? So folks, that is just a quick example and set of notes over the indefinite integral operator and definite integral operator, the process of anti-differentiation applied to a vector valued function, which gives rise to indefinite and definite integration. And that is how we perform that process. Now, there is some application to that calculation, and we will get into some of that application here in a few videos. I got a video coming up where we're going to look at the unit tangent vector, and we're going to be looking at doing some initial value problems with vector valued functions. All right. We're going to be getting a little bit into the interpretation of derivative calculations and integral calculations. And this is actually going to develop in the first of all, the calculus context, the math context, and then we're going to take it out to motion in space. And we're going to interpret it and develop it in motion in space. And then those ideas are also all going to bring about some other application that goes back kind of to the realm of calculus or mathematics, and we're going to look at things like curvature, and then return a little bit to motion in space and look at components of acceleration and all that good stuff. So that is what's coming up here in a few videos, actually in quite a few videos in the lineup. But I will end with this for today, folks. And I might have one more that I get posted up for you tonight. If not, look for it early sometime following this video. So, hope you're all doing well, hanging in there, and I'll see you in class very soon.